Okay, in this video we will be looking at the airplane example with the radar tracking device that we talked about in class. And in class we talked about really the hardest part of the problem, and that is saying when we look at acceleration pieces on this thing, we have a radial direction, we have a theta direction, that if we have any piece of acceleration in the radial direction, if the radial direction of acceleration is not zero, then none of the theta direction acceleration will cancel it because they're perpendicular to each other, and then so we would have some total acceleration. But this airplane is flying straight and level on a straight line path at constant velocity, and when you're moving on a straight line path at constant velocity, your acceleration is zero. So zooming in just a little bit to be able to read the problem statement. We saw it in class, but so we have a jet plane flying at a constant speed v at an altitude of h equal 10 kilometers. It's being tracked by radar located at point O, directly below the line of flight. If the angle theta is decreasing at a rate of 0.20 radians per second at the time when theta is 60 degrees, determine the value of r double dot at this instant and the magnitude of the velocity v. Let me just zoom in on that for a second, give you a chance to read that for just a second. And then I'll point out that over to the right we have a diagram that shows what is happening, airplane flying across, and from the argument made earlier, since the acceleration of this airplane is zero, then the radial piece of the acceleration must be zero, and the theta direction piece must be zero. Now we've been asked for two things: something related to acceleration, or double dot, and we've asked for something related to velocity. And we are in cylindrical coordinates because we were asked for the r double dot. So let's go take a look at the equation sheet and see what we can deal with. Here's the velocity equation. Here's the acceleration equation. We'll come back to the velocity in a minute, but we want something out of the acceleration equation. We want r double dot. Now, it only shows up in one place in the acceleration equation, and so this total thing is the acceleration in the e sub r radial direction, and we know that to be zero, so we're going to be able to write an equation just from this term that says this quantity in parentheses is zero. And so that's the way we'll start the solution to the problem. A sub r is equal to r double dot minus r theta dot squared is equal to zero. Okay, from that equation we can say that r double dot is equal to r theta dot squared at any instant. Looking at our geometry as a triangle, because we're going to need r, and we know our theta, 60 degrees, that was given. We're going to need r, but we can get that from the geometry. Okay, here's our angle theta. Here's our height h. Here's our distance r. We can bring h into this triangle right here. If it makes it a little bit easier to visualize, that is also h. And so we can say that h is equal to r times the sine of theta. Or we can say that r is h divided by sine of theta. Same thing. And we plug in theta equals 60 degrees, and we get that r is equal to 11.55 kilometers. Now, from our equation where we're hoping to solve for r double dot, we now know r. Now, theta dot was given to us in the problem, the 0.02 radians per second. So we now know both of these pieces. So r double dot is 11.55 kilometers times, and we can see from the picture that if the airplane is traveling forward, the theta dot that was given to us, theta must be decreasing. So that is going to be a negative value for the theta dot. So negative 0.02 is the truth, but we are going to square it, so that negative sign is going to go away. And we can get, therefore, that r double dot requested in the problem 4.62 times 10 to the minus 3 kilometers per second squared, or 4.62 meters per second squared, is r double dot, and that's one of the quantities that was requested. Then the next quantity that was requested was velocity. And so, looking at our picture, we have velocity, and our velocity can be divided into two pieces: a radial direction piece and a theta direction piece. Looking at the equation sheet, what we have for velocity, r dot, the velocity vector, is a radial direction piece, r dot, and a theta direction piece, r times theta dot. Okay? And this velocity, our radial direction piece, is the r dot that we just saw. The theta direction piece is the r theta dot piece. And so, using some of that geometry, what we'll be able to say is the piece of this velocity of this total velocity in the theta direction is a velocity times, let's see, where's our angle theta? Theta is here. Therefore, theta is here. Okay? Or theta is here. And so for this theta here, this piece would be the opposite piece. So v times the sine of that theta is equal to this piece. And this piece is the r theta dot piece. So v sine of theta is equal to the r theta dot piece. And we'll put magnitude around it, not worry about direction. And we don't know v, but we do know r. We've already solved for that, and the theta dot was given. And so now we know everything that we need to solve for v, and v is 0.267 kilometers per second. Oops, you can't see that, sorry. So v sine of theta r theta dot, rearrange it, solve for v, and get, excuse me, 0.267 kilometers per second. Let's zoom this out a little bit, getting a little crowded. Okay. Or if we want to convert to kilometers per hour, v is 960 kilometers per hour. That's pretty good speed. It's moving right along.